Uh, so would you like to start sharing the screen?
Yeah.
Introduce you. So our next speaker is Lin Xiao, who is working now at Facebook. He graduated from Stanford with Stephen Boyd and then he moved to have a postdoctoral position at Caltech, after which he started to work in Microsoft Research for 14 years. Among his awards, I should mention that he obtained the Test of Time Award at Neuro IPS last year for his work on the regularized dual averaging method for sparse online optimization. So I'm very happy to welcome you to our conference. Please, it's all yours.
Okay, thank you. Thank you for the introduction and thank you for the invitation. This work is actually, when I did this work is I finished at Microsoft Research. I just moved to Facebook, less than 3 months. So this joint work with Adrian Hendricks, Sebastian Bobek, Francis Bach, Laurent Vasuri. That's all my kind of French-speaking co-authors all at once. Okay, we're going to talk about statistical preconditioning for distributed empirical risk minimization. So the motivation is basically solving a large-scale empirical risk minimization. Here, we just minimize a empirical average of individual loss functions, each, associated with the data zi sampled from some unknown distribution. And you may have a regularization, which is a simple, like a L2 or L1 regularization. In this talk, we actually focus on only smooth convex losses functions, such as least squares or logistic regression. At the end of the talk, I will actually comment on extensions for non-convex deep learning type of work. So the idea of distributed ERM is that, when the data set is too large to fit in a single machine, which is, obviously the case for industry, problems like search, ranking, social network problems. In that case, suppose we just divide the data set to M machines. For each one have a local cost function fi. It has local number of Zij samples, but it's supposed to be just match this one. In this case, we assume that the total sample is capital N. So, but this local function can only be computed, accessed at the local machine. So, for example, when you have like hundreds of machines collaborate to work on solving this problem, you really need some communication efficient distributed algorithms. Very much the in most cases, communication is a very kind of a dominant factor. So let's see the most simplest idea if you want to do a distributed organization. For simplicity, I just remove the regularization. Let's just talk about all the smooth optimization part. And then you will, your data is stored on the machines. Then you have a server to do the computation, and you start with some initial point x0, and then you just broadcast to the servers. Each server can locally compute the gradient, and then send it back to the server. So the server basically can kind of aggregate the gradient, the total gradient here, average gradient here, and then you do gradient descent. So that's the basic, probably the most obvious thing to do. Here again, we, for simplicity, we just consider f is strongly convex. Usually that's the result with some kind of L2 regularization. And then the number of communication round in this case is actually same as the iteration complexity of your gradient descent method. For the classical gradient descent, you have this order of condition number kappa times log of 1 over epsilon. And if you can also replace this simple gradient here with Nesterov accelerated gradient methods, which will not cost you any more kind of communication. Locally, computation is also on the same order. You can actually get this square root of condition number. So when condition number is very large, that's usually the case for the large scale data set. And then you have got a dramatic increase. Indeed, if you are only allowed to access the first order oracles, then this cannot be improved in general. There's a lower bound results. So as we ask the question, how can we do communication efficient, more efficient than the one we see before, than the one on this, the complexity here. So we need to think about kind of more than a first order oracle. And the idea here is basically we do a statistical, the high level idea, we do a statistical preconditioning. Basically, we subsample some data, send it to the server, a very small number of them, compared to the total samples. And then we saw a subsampled empirical risk immunization at the server. And then that will help preconditioning the gradient descent method. And actually you will get iteration kind of a complexity of the number of communication rounds, very similar before, but is replace the kappa as a different kappa prime, a preconditioned condition number, usually can be much smaller than kappa. So this is a high level idea. And so the talk will just actually, in the first part, which focus on the preconditioned gradient methods. Actually, this part, even the second part, how do you do statistical precondition, they do not, has to do with distributed optimization. As you can see, it is more general than distributed optimization. You can use it for even sequential or other purposes. But for distributed optimization, this is a very kind of a straightforward, intuitive application. Then after that, I will talk about preconditioned accelerated gradient methods. So this is quite interesting because we all know, preconditioned conjugate gradient methods. In fact, you can view the accelerated gradient methods as an extension of a conjugate gradient methods to the non-quadratic case. You can have a convergence risk depending on square root of the condition number. But interestingly, that has not been done for the accelerated gradient methods. Basically, for non-quadratic, it has not really been shown the square root condition number convergence. I will, have a more comment on this one because there's not a clean solution indeed. Okay, let's start with the preconditioned gradient methods. So for simplicity, let's just focus on minimize the smooth and strongly convex function. The hashing has a lower bound, upper bound of the eigenvalues, sigma and L, for all the points in your constraint. In your constraint set, that could be for all the RD. So this is a standard gradient descent with step size epsilon, eta t. And if you consider Nesterov accelerated methods, you have this extrapolation point before you take the gradient. This is one of the simplest versions of Nesterov's method. There's many, several other different versions can achieve the same complexity. Of course, you have stochastic gradient, with momentum, items which are very popular in deep learning these days. But for this talk, we'll only focus on the, say, batch, full gradient methods. Again, I will discuss some comments at the end. So the condition number is, a very classical notion. It's basically defined as, ratio between the largest eigenvalue bound over the, bound on the smallest eigenvalue. When the condition number is small, you can see its gradient descent will, have a nice landscape to converge with very few iterations. when the condition number is large, you could have this kind of a zigzag behavior causing slow convergence. And so the iterated complexity, in order to reach this objective function less than epsilon, that's the one I showed before. Preconditioning, is very kind of a powerful technique in computational mathematics. It's basically a computationally efficient way to reduce the condition number. So if you reduce the condition number, then you can apply either gradient or accelerated gradient. You just improve all the result across the board. But the step to do computation better to be efficient. Otherwise, it destroys the purpose of speed up. So let's look at a more general version of gradient descent. Is basically proximal gradient descent. That's the case when you have a kind of a non-smooth regularization function psi here, like L1. In this case, the generalization of gradient descent is called as a proximal gradient descent. Is basically you linearize the smooth part function, and you keep the non-smooth part intact here, and you add a quadratic penalty from moving away from your current point. This eta t is the step size. So you can easily say if this psi equals 0, then this is the same as a gradient descent. And you can show that the convergence of these methods is very similar. It is basically have this kind of geometric convergence, linear convergence. Here I put this f as a subscript for the condition number. Basically, this complexity has only to do with the condition number of the smooth part, and it usually does not have anything to do with this non-smooth part, because you put the whole thing in each minimization. So that's what you get. Similarly, there's an accelerated version. You get a similar condition number. Okay, so that's the algorithm we're gonna work on. It's a little bit more general than the gradient descent. So in order to talk about preconditioning, we're gonna talk about something called a relative condition number. So we need to have a reference function phi, which is also differentiable surrounding convex, and it similarly has a lower upper bound on its eigenvalues, and you can define a condition number. Then the relative smoothness and the relative strong convexity basically defined in this way. So your target objective function, the hashing, is a lower bounded and upper bounded by the hashing of the reference function with some coefficient. So this is sigma is a relative kind of a smallest eigenvalue, smallest relative eigenvalue, something like that. And this is the largest relative eigenvalue. And you can have this relative condition number defined. So for example, if you use reference function, it's just the Euro squared Euclidean norm, then you get the classical definition. Basically, you can omitting the over phi, because phi is just simple, and it's just classical definite condition number. And if you put the reference number as the function itself, of course, you get a relevant condition number is 1. So there are equivalent definitions of this. So this is very convenient if you're dealing with, say, quadratics or functions. So there's an equivalent definition is in terms of Bregman divergence. So for the reference function, you can always define the Bregman divergence in this way. Basically, the function, the difference between the function and the linear approximation at x. So you can equivalently express the relative smooth and relative strong convexity in this form. Basically, the bounding the Bregman divergence. And by using this, you can have more kind of, especially you can actually working with something that is very popular in machine learning, use entropy, kind of KL divergence type of things. Okay, now precondition is very simple in this framework. You basically replace, remember this is a precondition, this is a proximal gradient method where before it was like the Euclidean distance squared. you replace that by just the bracket divergence of the function. And then you can show that the convergence rate with a step size which is 1 over the relative Lipschitz constant. So you got a linear convergence. There, your dependency is only on the relative condition number. Of course, how do you solve this argument problem can be more complex. I will discuss that later. At least this is the number of iterations you would, if you consider this as a subproblem locally. Some examples, like if you define phi of x reference function as your local quadratic based on hashing, you got Newton methods. And also you have some other approximations. You can use like a quasi-Newton methods, something like that. But usually those are very costly in a high dimensional setting. So okay, so this is a general setup. Next, we're going to talk about what do we call statistical preconditioning. So there's an intrinsic structure of averaging lots of loss functions. That's a very kind of particular structure, actually a dominant structure in machine learning, in data science. And then subsampling is a very natural idea. So you basically can approximate this overall empirical loss by a subsampled loss. Then there's a simple lemma, says that if you can approximate if your approximation, the hashing can be approximated reasonably well, this is the spectral norm of the difference of the hashings. And let's say you can approximate to the extent that the upper bounded, the difference is upper bounded by mu. And you choose the reference function is the small approximation plus a extra kind of a regularization. This is mu. This mu is the same as what you can approximate. And then you get this simple expression. Basically, is upper bounded by a coefficient 1. Here, the lower bound is basically this simple ratio here. And if you're gonna calculate the condition number, is very kind of simple expression is 1 plus this mu over sigma f. Sigma f is smallest eigenvalue of your original function, and mu is how good you can approximate. So it makes sense. If you can approximate this hashing function up to its smallest eigenvalue, then you basically get a constant relative condition number. Okay, let's go through some simple calculations. Now we just want to find a approximation bound using subsample the hashing to the original hashing. The classical result. Now we can apply just matrix Hoyle-Fitting inequality, which I think Rachel Ward talked about. Lots of matrix concentrations were powerful in streaming algorithms. In this case, we can use matrix Hoyle-Fitting, just directly get this this upper bound. So you have some log in terms of dimension and the probability margin, and then it's kind of one was square root n kind of scaling. So L is basically can view as a upper bound on the individual hashings. So that's basically the mu. This is the mu is basically decreases with 1 over square root n if you increase the sample. In this case, you can easily calculate the relative condition number, which usually you assume that the smallest eigenvalue are the same because they are all come from the regularization. So that's usually easy to obtain. And then you get this relative condition number. As you can see, if you with a large sample, your relative condition number can be smaller than your sometimes can be much smaller than your original condition number. So that's basically you can use some classical result which has been obtained before. So there's a caveat that, okay, in order for this argument, the condition number to be true, we need this kind of red star equation to hold for all x in your domain, because you have a dynamic stochastic gradient descent algorithm. You need to make sure that at any point you touch on or in the domain, this holds, this inequality holds. So for quadratic, that's not a problem, because the hashings are constant, independent of x. So you can easily obtain this relative condition number. But for non-quadratic losses, your x changes and your hashing changes. So you have to impose some kind of a higher order Lipschitz constant on hashings. Even in that case, the argument usually to obtain a union bound, using ball packing ideas in high dimension, you will encounter a additional square root of d. D is the dimension factor. So in that case, usually you will get a relative condition number, which is on the order of square root of d over n. So this says that the benefit precondition may degrade in high dimensional very fast. Indeed, we have lots of the problems in very large scale in online kind of click-through predictions where d and n are both can be billions, and they actually cancel each other. So basically, this method will not work. But in practice, we always observe, it would just, the performance is always getting better if you just using more samples. So the d is not there. So that comes to so up to here, this is kind of a previous work. You can, although some of them are not explicitly stated in previous work, but that's basically previous art. So the main result we obtain, the first main result we obtain in this work is basically you focus on linear predictions. That's why we restricted in the beginning, say, is convex models. Those are like least squares or logistic regression. In that case, they have a very special structure, and you can imagine the hashings are basically summation of the other products of rank 1 matrices. In that case, you can actually improve the factor by square root n. So that's the first result for quadratic loss. So R is basically the upper bound on the norm of the feature vector. Instead of square root n, we get a 1 over n. This is a much better improvement. And for non-quadratics, again, by exploring the structure that you got this linear composition of a scalar function. Your hashing is a average of rank 1 matrices. You can actually get rid of the dependence on D in your concentration map. So that's both are quite a significant improvement from the previous estimations. So I will not talk about the details how we get this bound. For this one, we use some kind of a transform the matrices and then apply matrix Bernstein inequality. For this one is more complicated. My co-authors are the ones that are really experts on this concentration inequality. Use quite a few some more kind of recent development in statistics concentration bounds. Okay, now let's talk about, we have this kind of improvement in terms of concentration bound. Basically says that this subsampling idea would really work well in terms of reducing the condition numbers. Now let's see how we can use it in distributed optimization. So distributed empirical optimization, this is basically recap of the before setting. You have total capital N samples, but they are too large. You store them on M machines, and that's how you want to minimize this function. So this is a similar picture as before. Again, all the M machines are responsible for compute the local gradient and send it back. But then this server will do this precondition distributed gradient method. In order to do this, so this is Bragg divergence of the reference function phi. So the idea is that the server will subsample n examples from all machines, once before everything starts. Just do ID sample with n of them. Small, little n can be very small compared to the total number. And once those reference point are sampled at the server can solve this problem locally. This problem doesn't have a closed form solution, so you still need solving a integral risk minimization problem only with little n samples, and also a much stronger regularization. Remember, we assimilated the Euro regularization you would put on a integral risk minimization inside this individual loss functions, but this is just extra regularization. So small samples, stronger regularization, which means this problem is way much easier to solve than the overall one. You can solve it locally. Indeed, the complexity for solving this are these randomized algorithms. Given n samples, suppose because this is your local function, its condition number is kappa of phi, is also relatively small as compared with the overall condition number. And you can have actually n plus condition number. So this is also, I will not mention, this is kind of the lots of progress made in the machine learning community or optimization community in the past, I would say, 7 or 8 years, the improvement. Because you can imagine for solving this problem, if you apply, even for the quadratic problem, if you apply for the conjugated gradient, you will get n times square root of kappa, right? So still you got a multiplication between them. But with this is actually all are randomized algorithms. You can get this n plus kappa, which is usually much easier. In practice, actually, we only need to it's basically n. Just go through the local data once or twice, then you're done. So in that case, number of communication rounds, it becomes, this is basically locally how much computation costs. But now let's see the broadcast and reduced number of things you have to do is proportional to the relative condition number. And there's a very clear trade-off here. Basically, if you sample very small n, and then your approximation is not good, so your bound mu is large. But the mu large has two consequences. One is that the local regularization mu is large, so the local kappa is very small and easy to solve. On the other hand, your relative condition number is large. So that means your local computation cost is low, but your kind of global communication runs need more runs to communicate. And on the other hand, if you use large samples, you will have like a increased local cost, much smaller communication iterations. And indeed, interestingly, roughly speaking, you have these two are multiplied together. So basically, mathematically, they're close. Basically, the condition number of your overall function is basically the multiplication of your relative condition number times the reference condition number. Of course, when in practice, you have to factor in how much cost in real time in order to pick the right amount of samples. Okay, so this is basically for the setup of preconditioned gradient methods, and this complexity is proportional to the condition number. As we mentioned before, in the beginning, you can use kind of accelerated gradient type of methods to make it dependent on square root of kappa. So that's the basic idea. And very interestingly, in this case, is not easy to do. It's hard, I have to say. I will explain a little more why later. But let's see, how do you do it? From a kind of algorithm perspective, there's not too much. You basically can mimic the preconditioning steps in the gradient step, or you can mimic combine with how do you do preconditioned conjugated gradient methods, and then you should assemble them together. You should get a accelerated preconditioned version. So this is what we do. We call it statistical preconditioned accelerated gradient methods. So this one, you don't have to know why. I'm just writing a bunch of scalars. Everything is a scalar, so very easy to compute. If you know Nistrov's algorithm before, still, this is a more complicated version of the Nistrov algorithm. So these are very easy to compute scalars. And then this is a whole algorithm, but you don't have to, as I said, you don't need to understand what the scalars are. If you have no Nistrov algorithm before, then you probably know this, all they look very similar. If you haven't seen the form before, then it's very hard to explain it, I have to say. But the main thing is, so on the other hand, basically a bunch of scalars, as you can see, each step you compute, even GT is another scalar. You compute a bunch of scalars, you solve some, find some AT plus 1, this is also a scalar quadratic function, very easy. And then you do some kind of a vector combinations. Those are just, add multiplication, addition of vectors, and also this one, convex combinations. The only thing that is kind of non-trivial is this step, is the local problem you're going to solve, which is indeed very similar to the proximal gradient method before. You have the linearization of the overall loss function, but this one is you need kind of a required communication to obtain assembled total gradient from the kind of different workers who has the data. And the server, you get the aggregated gradient, and this is the linearization part. And again, this one could be L1, you can put it there. And before, we only have one term, says a divergence of the reference function. With respect to, actually, before we only have this term, with respect to the YT, where you take the gradient. But in the accelerated gradient method, you split this into two parts. Actually, it's a convex, combination of two terms. The other one is actually reference to a different point, which is VT, especially the previous one of this one. But the gradient here is on a different vector. So that's all the kind of mysteries in Nistrov's accelerated gradient methods. But computationally, that's basically, you can imagine this is also requires you to solving a local empirical, small empirical risk minimization problems. Actually, the complexity would be the same as you saw in the non-accelerated version, even though you have two terms, but you can just combine them. So there's a G, there's a scalar G, actually, it's kind of a line search. If you know line search in optimization, basically you are not sure the step size, and you always try a larger one. But if it doesn't reduce your objective function, you will just cut it by half, and you try it again until it reduces your kind of objective function. The reason you always want to try a larger one to reduce it is because large steps usually give you a faster progress. And yeah, so in here, each step we just trying to always increase it, and it will satisfy some condition. If some condition is not satisfied, we'll just have to cut it by half. So this basic answer is a scalar GT. Here, no, again, this is, I do not expect you to understand why the GT is here, but just because the theory will have something on GT, a scalar. So that's another main result of this work is basically the convergence of this preconditioned accelerated gradient methods. Indeed, at this stage, I have to say that this works for any preconditioner. You don't have to say you can apply this to a different context where you have certain preconditioner constructed from different perspectives, not necessary for empirical immunization, not necessary for subsampling. This result works for any kind of preconditioning. So the convergence is basically, is a multiplication of these convergence factors at each step. So you notice that's why there's a G of tau here. So without G of tau, if this one is 1 or the constant, we can just say this is 1 minus 1 square root kappa to the tth power. So the linear convergence with a kind of square root of condition number complexity. And for this one, of course, you would expect that for quadratic functions, we got this G, this factor here is 1 all the time. But for non-quadratics, there's some complication. Basically, you cannot bound. It's hard to bound them in the beginning, depending on your reference function. Oh, actually, not too hard. I have a bound here, a trivial bound here. But this factors always go to 1 geometrically fast. And indeed, you can always upper bound it by the local reference function. In that case, so there's a multiplication of these two factors, basically under the square root is, roughly the condition number of your original function without precondition. So that's the worst case. But that's only happens possible to happen in the kind of beginning of the algorithm, because we can show that this one will just go to 1 very fast geometrically. Moreover, this one, as we can see, is explicitly, this is not some magical parameter. We don't know. This is one is calculated as distribution, as actually is required in the algorithm to calculate it. So when this one is small, you can know that gives you the numerical certificate that you are converging at a very fast rate in terms of the square root of the relative condition number. And this is actually in the case, we always observe this is 1. I mean, 1. You can make it less than 1, actually. So now let's mention some theoretical challenges for why we cannot get a very clean solution. So for the quadratic case, as you can see, we have a clean solution. Basically, that's same complexity as conjugated gradient methods. Of course, it applies for preconditioning as well. But for the non-quadratic case, we lose some kind of the analytical kind of a convenience of the kind of Euclidean norm distance squared, and then acceleration actually is quite difficult in general. Actually, there's negative results recently saying that in the relative smooth and relative strong convex setting, the best you can do is actually the linear convergence with without acceleration. Basically, you cannot do this in general. So there's a negative result. But in this case, we actually can obtain asymptotic acceleration when phi is strong convex, with strongly convex. So this result, negative result, said that for any phi only need to be kind of strictly convex, do not need to be strongly convex. But if we can impose phi is actually strongly convex, we can actually get asymptotic acceleration in theory. And in practice, we always observe clean acceleration all the time. Maybe there's more to do in the theoretical side as well. Okay, now this is basically how we're going to use this algorithm for distributed empirical risk minimization. This is very similar as before. You still get the local workers to compute the gradient, and then notice here is a yt. It's no longer xt. This is a yt, and this algorithm basically maintains 3 sequences: xt, yt, vt at the server. You do pre-sampling again, same as before, as a reference function. writing here. And again, the local problem, as I said, solving this one is basically the same as before. And the difference is that here is the number of communication run will become roughly square root of the relatively condition number. So this is improvement from before. You could only get a proportional to the relatively condition number itself. Okay, there's some numerical examples on some logistic regression on some data set with I guess 47,000 600,000 is capital N. This one is really not large. You could just store everything in one computer, but we just doing this as in a distributed setting as a demonstration. The regularization usually is very, very small. And the condition number can be large, and the convergence, if you run first order algorithm, usually is quite slow. But then we just do like 10,000 subsampling at the server. I think this one maybe on actually on how many machines is irrelevant. As you can see from the analysis, the analysis is basically said you obtain all the aggregated readings. How many machines you got is just irrelevant. We can experiment. That's the choice of the mu, because mu is the one parameter we are really not sure. We can only estimate and do lots of experiment. We got a rule of thumb is essentially kind of 1/n level for your mu. That would be really behave good. For example, if mu is too small, basically your local problem is a yield condition. You cannot really solve the local. You cannot really solve this local problem accurately enough, and then you have a problem because that's why you have. If you cannot solve the local problem accurately enough, then your kind of global solution will very low quality. And if you have increased the regularization, then your local problem can be very easily solved. I guess in this case, we only did like 2 or 3 iterations of two or three passes over the local data. And if you increase the mu too big, then that's also bad, because this is predicted by theory. The number of iterations will increase. There's more experiment with different methods. This black line with a cross up here, that is actually accelerated gradient method without preconditioning. So as you can see, the other methods are preconditioned method. So this is the black dashed line is our not black. Actually, that's a very confusing color scheme, I have to say. So all the others are preconditioned methods. The first one, the solid lines are all kind of non-accelerated. The other two accelerated variants with some. But for this one, like a KDD 2010, you have a 20 million dimension and 7 million data set, still considered small. And those are the actually public data set available. Lots of the industry really large data set are not publicly available. So for these ones, you can see, I guess the regularization for this one is like 10 to -8. And if you use this kind of algorithm, as you can see, the most impressive thing is that you can always get maybe over, very accurate solution. You may not be necessary even within, 40 or 60 iterations. That's it. That's because of the preconditioning, power of the preconditioning. So basically, if you want to run a cluster of compute machines, you want to say they will have to do some kind of reduce and communication. That's only a constant number. Okay, here is basically the gain, which we from the experiment is only just 1, roughly 1 always. Even if you run it long, usually we'll stop here like 50 iteration, everything that. But even if you run it long enough, you will get very stabilized. Okay, I think now its time is over. I will just summarize it. So this work we introduced 2 improvements. One is basically the significantly improve the bound on the relative condition number by exploiting the ideas of the linear models like logistic regression. And the other one is relatively smooth and convex setting. We have this preconditioned acceleration method have asymptotic acceleration, and combine them together, you will always get kind of high precision solution for a few tens of iterations. Okay, maybe I will just have a comments on the. I will skip this part. Let's just on this part on non-convex optimization. I think this can be extended for non-convex optimization because the preconditioning idea is a local. I mean, it works locally on your iterates. The reason we did this convex setting is basically can have a beautiful, nice kind of a complexity theory. But if you are just really pay attention in practice how you improve your computing, and then I think it can be done. In fact, if you talk about the most kind of popular stochastic optimization practice, ADAM is actually a diagonal preconditioning. You can see that. But there is a trick is how do you construct the preconditioner? So in that perspective, I believe a very efficient low rank plus diagonal preconditioner can work better. Of course, the challenge here is that as in this work, we talk about at each step, you just, using a mini batch, sample, a fixed sample even, you calculate the preconditioner repeatedly on those examples. In deep learning cases, you probably cannot afford that. And you could probably have to rely on history. Instead of for each new point, you recalculate a mini batch gradient, you probably have to rely on a history of accumulations of the stochastic gradients, which is exactly what ADAM is doing. And that's part of the future work. Actually, I'm already working on it. It's current work. Thank you.
Thank you very much. I have a question about this price that you pay in communication versus computation on a local machine. Do people consider communication between machines themselves? Maybe you can compute your gradient and send it to your neighbors, and that improves. And then you don't connect to the server, and that's another way to improve efficiency.
Yes.
Or maybe multi-scale, several steps of servers, and then at each set there is less communication.
Okay, good. I think the multi-scale idea I have not thought about before, because that's as you can see, that's when you're doing multi-scale thing, you must be doing some kind of preconditioning could dramatically improve your thing, your results. But there actually has a lot of work in academia, especially on distributed optimization, where you basically do peer-to-peer communications, and you assume asynchronous. As you can notice, this work requires synchronous updates. But it's okay because if we only have like 50 of them, I mean, you can tolerate that. But once you do those asynchronous kind of peer-to-peer communication, and you can see that actually, myself also did a lot of work on that. Even wrote a parameter server kind of asynchronous computing myself. Theoretically, both from theoretical and practical point of view, those are not very competitive with this kind of computing. Actually, it's far more worse. In my experience, the gap is not an order of magnitude, like several order of magnitude difference you can resulting from there. That especially in the data center, well controlled. For example, you have a huge kind of corporation like Microsoft or Facebook, they have all the data, they want to do some batch training, then this usually can be much faster. The asynchronous ones, there also has their useful places. For example, in so-called these days kind of a federated learning, where you relies on computation, distributed computation on individual devices which are not accessible, very low computational, asynchronous has to be allowed. But that's, that's intentionally designed for the slow conversion. But if you are, you have all your data all together, you just want to have a solution as fast as possible. This kind of batch methods usually is much faster.
And one more question. So you mentioned in the end that you could work not necessarily with convex functions. So does Nesterov trick work for example, finding a saddle points or something like that? Or is it, I thought it was just purely convex.
Yes, for the theory to work is all in the, actually I have to take back, there are recent work even for the non-convex problem, where the objective is basically to reduce your gradient to 0, right? Is find a station, not to find a minimum. Even in that case, certain variance on Nesterov's acceleration actually is better in theory. It's but the improvement is not as dramatic as in the convex case. I forgot how much the improvement in theory you can prove, but I don't know how it works in practice. But more importantly, I think for the large scale things, especially in deep learning, everything depends on stochastic gradient type of method. In that case, Nesterov acceleration, at least in theory, is that there's not really clear acceleration, but in practice, is basically somewhat equivalent to the momentum people use in stochastic gradient descent. Essentially, kind of filtering of your stochastic gradient to do a little bit of variance reduction and stabilization. That's actually the default method, even Adam using the momentum.
Can I read a question from the audience?
Yeah, sure.
So in conventional settings, effective preconditioners are often tied to the underlying applications.
Yeah.
So it seems here that the idea is derived from the loss function without any reference to the underlying problem. Do you think it's possible to incorporate information about the application into this approach?
Actually, in this case, we already incorporated, let's see, structure. So exactly, and precondition usually is ours, depends on the problem. If I'm gonna say only minimize, for example, fx, I do not tell you what fx is, then you probably have no idea what a good efficient condition. But here we precisely explore the idea that is an empirical average, and subsampling is actually the most obvious, powerful way to do preconditioning. Even in this, for example, in this, as I said, if you do, this is already the structural problem. That's why we can do subsampling as a precondition. But even this, as I show here, if you do not assume more, if you only assume the kind of a empirical average, that's the rate you can get. Square root of 1 or square root of n, and there's condition square root of dimension there. So we use additional structure basically for that's why we consider logistic regression types of things is a composition of linear scalar function with a matrix feature vector weight product. If you have this structure, then that's actually the precondition you can expect. So in both cases we actually used lots of problem structure.
So John, can I ask a question?
Go ahead, Lin Xiao.
So it's great talk. Thank you. So this this statistical precondition using this Bergman distance, you have to invert the gradient of phi, right? You gradient f, gradient phi.
Yeah.
But for a special application, but is that a practical way of doing business, or you have to invert that?
Yeah. So that's basically that's basically here. So here, yeah, for example, if this is let's say this in the quadratic case, this Brackman divergence basically a matrix, right? Basically is a matrix constructed by the subsamples, and you should invert it. But this,
well, this that's as expensive as invert the whole data set for it.
no, this is basically invert. I got it. It's basically in terms of dimension, they're the same.
Yeah,
but
the dimension is the same. Yes, you don't. Well, it takes a little less time to evaluate the gradient, but because you have a fewer data set.
Yeah, yeah.
Okay,
But then
you don't save anything, do you?
no, this here, that's here. See, this is the conclusion.
How do you invert gradient phi? How do you invert gradient phi in practice?
Oh, you just solve this. You solve this. If you want to invert a matrix, we do not explicitly invert it. We basically transform this. Say, hey, this is you are minimizing a quadratic optimization problem. This quadratic optimization problem has dimension d
with a huge matrix.
Okay. has this structure. So this is your phi. This structure. If this structure, then that's your cost of inversion. Is
Okay.
n plus kappa phi, has nothing to do with dimension.
Okay, I understand. Okay, then I just have another question that always bothers me. If you're in the machine learning, as maybe the deep learning, this is, as I assume, this is a very year conditioned, right? This loss function. But in practice, it's only, in one sweep is like one epoch. There's only like 300 epochs, even the ImageNet.
Yeah.
It's kind of maybe the preconditioning, you don't need that. Because another way to put it is that you have to worry about the generalization accuracy, which you didn't talk about it.
Yeah, exactly.
But, for some crazy reason, which I don't understand, this deep learning is very year conditioned, but it only takes 300 iterations.
Yeah, exactly. That's
inside of that.
Yeah, okay. That's exactly your point. So basically what I show here, like 10 to the negative 10 accuracy, no one could care, right? And you do not need this accuracy from machine learning theory perspective, from generalization theory perspective. But let me tell you, the experience is that if you have like
sorry, is that training or generalization?
Training, all the training.
This is training.
Okay.
Yeah, we basically can. Well, no, as I talked with Jin Chao before, I mean, we basically have no effective way to control generalization in general. Mostly is based on empirical generalizations. What I can tell you is that you generally really don't need this kind of precision. But imagine you have a billion, hundreds of billions samples. Huge dimension. You essentially capture everything. And if you with your generalization theory, your generalization error 1/, several billions, that's almost very, very tiny. Basically saying, when you have a huge, when it's like stochastic optimization. If your number of samples go to infinity, I mean, what you do is exactly the generalization error anyway. So this is one argument. The second argument is more kind of practical, is that as Microsoft, Google, or Facebook, they put this thing in production and say, okay, maybe we do not need that precision. But what if we just go that precision and we try? Oh, see, you see, actually there's like 0.1 increase in your revenue, right? Oh man, that's how many $1 million. I mean, people do care. I mean, if you can get this empirically, that's still doable.
The mystery to me is that this let's forget about the generalization accuracy. That's too subtle, too difficult. This is a training accuracy. If you even train even ImageNet, it takes 300, maybe 300 iteration. If you think about one epoch is one iteration.
Yeah.
To get almost 100% accuracy.
Yeah.
So you have a terrible, this means that this machine learning stuff people are crazy about is a very low bar. 1,000 class is no big deal. It's you don't really need much accuracy to get anywhere. There's no way you get to a global minimal, but somehow it is just accurate enough for the training accuracy. And it's a terrible year condition problem, but somehow for 300 iterations, you get the job done. It's a contradiction, don't you think so? It's just the mathematics that makes no sense, except you only need a very, very rough accuracy to get the classification right. Because you don't, after all, you don't really, it's not really AI, you know, 1,000 classification is not really AI. People are crazy about it. If you have a robot that can only tell only 1,000 things, but it's not a big deal. But anyway, but I'm sorry, I just have this dilemma. Well, you know, I know time is running out and got excited, but.
Yeah, there's lots of, I think the theory is one perspective, but in lots of applications, it depends on your application, how going to use it, how serious is to your business.
Thank you very much again. Thank you. This made me think a lot of things. Thank you.
Thank you so much. And